Okay, let's just jump right straight into this explainer. Today, we're going to see exactly how scientists measure our planet's surface temperature using this totally brilliant recipe of math, invisible light, and code. Because, understanding the heat radiating off our planet isn't just about figuring out if you need to pack a lighter sweater today. It is absolutely crucial for tracking massive global climate shifts, predicting agricultural crop yields, and mapping out those really dangerous urban heat islands in major cities. So, welcome to Earth's digital thermometer. Imagine for a second trying to figure out exactly how hot the ground is across the entire Rasta region, and not just for one afternoon, but for every single day of the entire year of 2019. Oh, and you have to do this without ever setting foot there or, jabbing a giant physical thermometer into the dirt. I mean, how do you take the Earth's temperature from 400 miles away, literally staring down through the freezing, empty vacuum of space? We're talking about capturing perfectly precise thermal data across thousands of square miles. It sounds a bit like science fiction, right? But it's actually just highly structured, fascinating logic. The secret is you don't need a physical thermometer at all. You just need code. Instead of relying on a bunch of weather stations and physical sensors scattered everywhere across the landscape, we use a really sophisticated data recipe written in JavaScript for Google Earth Engine. If you aren't familiar with it, Google Earth Engine is this massive planetary-scale platform for Earth science data that lets analysts compute literally petabytes of satellite imagery. It's the engine that allows us to take all these raw and visible data points and transform them into a vibrant, highly accurate thermal map. So to pull this off, our recipe follows 5 steps today: reading Earth's thermometer, cleaning the satellite view, looking at the power of plants, calculating surface temperature, and finally, painting the heat map. That's our complete step-by-step guide to take us from importing raw pixels all the way to a finished, mathematically perfect visualization. Let's kick things off with Section 1, Reading Earth's Thermometer, where we gather our raw ingredients. Our source code starts by pulling in an entire year of data from the Landsat 8 satellite. Landsat 8 is essentially this wildly powerful digital eye in the sky that continuously orbits the Earth, snapping pictures in wavelengths that human eyes can't even see. Specifically, the script zeroes in on a shapefile boundary for the Rasta region, capturing everything between January 1st and December 31st of 2019. This massive pile of imagery is the foundation of the whole project. It's the raw material we absolutely have to start computing. Moving right along to Section 2, Cleaning the Satellite View. Basically, washing our ingredients. Because let's face it, raw satellite data is a complete mess. You can't just glance at it and get a temperature reading. It is totally full of photobombing clouds and their dark shadows. Think about it. If the satellite measured the top of a fluffy, high-altitude cloud instead of the actual dirt down below it, the reading would come back freezing cold, and that would completely ruin our ground map. So the algorithm fixes this using a function called cloud mask with specific bit masks. It targets bit 3 for shadows and bit 5 for clouds to literally erase them from the dataset, leaving us with clean, totally usable surface pixels. To further prep the image, the algorithm applies what are known as scaling factors. It multiplies the optical bands by 0.0000275 and subtracts zero point 0.2. Now, you might be wondering, why on earth do we do that? Well, raw satellite data is heavily compressed for its long journey through space, so it needs to be unpacked back into true, usable numbers once it reaches us here on Earth. After that unpacking, the code scales the thermal bands, scrubs out the clouds like we just talked about, calculates the median pixel value for the entire year to get a rock-solid baseline, and finally clips everything perfectly to our raw shot boundary. All right, Section 3, the power of plants. And this is where things get really fascinating. Because to figure out how hot the ground is, we actually have to measure the plants first. We do this by calculating the NDVI, or the Normalized Difference Vegetation Index. It's a calculation that uses satellite bands 5 and 4 to measure the exact health and density of vegetation in our specific area. Fun fact, this is the exact same tax scientists use to track global deforestation or check in on crop health. The code grades the plant life on a scale from -1 to 1 and uses a visual palette of blue, white, and green so we can literally see the foliage density from space. I absolutely love this next part because we get a fun little glimpse behind the curtain of the code itself. The exact line of JavaScript reads map.addLayer, NDVI, NDVI palette, and then the label NDVI Bangkok. We can so clearly see the human side of coding here, right? A stray developer comment playfully labeling this visualization Bangkok, even though our target area is very clearly the Raw Hat region. It's just a great reminder that real humans, with all our little quirks and copy-paste errors, are the ones writing these insanely complex planetary algorithms. Next up, we take that plant data and calculate the fraction of vegetation, or FV. The math for this needs the absolute minimum NDVI value in the area, the maximum NDVI value, and then it divides the differences and scales it exponentially by the power of 2. It sounds complicated, but it's not just a fancy math trick. It's actually a way of determining exactly how much of a single tiny satellite pixel is covered by a cool, leafy canopy versus just exposed, sun-baked dirt. That gives us a complete fractional map of the area's greenery. So why do we care so much about this leafiness fraction? One word: emissivity. Emissivity is the Earth's unique heat signature. It represents exactly how effectively different physical surfaces emit thermal energy. Think about walking barefoot on a dark asphalt parking lot in the middle of July and then stepping onto a cool, grassy park right next door. They absorb and release heat totally differently. This vegetation fraction allows us to mathematically nail down the exact thermal signature of the specific patch of ground we are analyzing. We calculate this emissivity using a very specific formula, 0.004 times the fraction of vegetation we just found plus 0.986. Essentially, we are combining a base surface value of 0.986 with a 0.004 modifier that specifically accounts for the variations in the plant life we just measured. Because plants hold moisture and cast shade, they fundamentally alter the physics of the ground underneath them. This equation perfectly captures that reality. Moving into Section 4, Calculating Surface Temperature. It's finally time to cook with physics. With our ingredients prepped and our emissivity calculated, we hit the climax of our data processing pipeline. The script takes band 10, which is the raw thermal band beamed down from the satellite, and runs it through an absolute monster of a logarithmic equation right alongside our plant-based emissivity data to unlock the raw surface temperature. It is an imposing piece of math for sure, but it beautifully ties everything we've built so far together into one output. But honestly, the real hero here is the number -273.15. The real magic happens with this simple subtraction at the very end of the code. All that complex math we just did, it gave us a temperature in scientific Kelvin, which, let's be honest, isn't very intuitive for most of us. Subtracting 273.15 acts as the ultimate translation key, instantly turning that Kelvin into the everyday Celsius degrees we all understand and can immediately interpret on a map. And finally, Section 5, Painting the Heat Map. Let's plate this data recipe and serve up the final visual. The visualizer takes our lowest calculated temperature, which was 18.47 degrees Celsius, and paints it with cool blue hex codes. Then it maps our absolute maximum temperature of almost 43 degrees, 42.86 to be exact, to scorching red hex codes, generating a whole gradient of greens, yellows, and oranges in between. It is amazing how visual gradients like this can instantly take millions of abstract, boring spreadsheet numbers and turn them into an intuitive story that human eyes just instantly understand. And boom, here is our final thermal output map. Now, curiously, you'll notice it's labeled as Land Surface Temperature 2023 in the code, despite us specifically filtering for 2019 satellite data at the very beginning. Yep, another funny little human quirk left in the script. But regardless of the typo, it proves beyond a doubt that code can paint a vivid, wildly accurate, and deeply mathematical picture of our physical world. Which really leaves us with a massive question to ponder. If a few lines of JavaScript code can perfectly reconstruct the precise heat of 2019 from 400 miles above the Earth, what will these exact same algorithms show us about our Earth tomorrow? As we wrap up this explainer, it's pretty clear just how incredibly vital these digital recipes are going to become for tracking the future of our changing climate. Thanks so much for learning with me today.